When Artemis 1 lifted off the pad, it executed a near-perfect test flight. It spent weeks in space and traveled further than any spacecraft designed for humans had ever gone. But there is a crucial detail about that flight. The capsule was completely empty. It was a brilliantly engineered automated machine, but it didn't have to keep a crew alive. We haven't sent people to lunar space in over 50 years, and even during the peak of the Apollo program, the longest we ever kept a human on the moon was just 72 hours. Adding a crew introduces a volatile biological variable that complicates every engineering decision. Life support, radiation shielding, and physical safety now dictate the mission parameters alongside thrust and trajectory. Artemis 2 functions as the ultimate high-stakes proving ground. It exists to verify that our technology can sustain human life in deep space before we commit to the lunar surface or the journey to Mars. The heavy lifting for that survival happens in the lower half of the Orion spacecraft. This is the European service module. For 10 days, this module has to operate a perfectly balanced closed-loop life support system. Out in the vacuum of space, there is no margin for error. This schematic shows the environmental control routing. The system has to continuously pull air through mechanical scrubbers to filter out the deadly carbon dioxide the crew exhales, while constantly managing the ambient humidity. Running right alongside those air scrubbers are dedicated recycling loops that continuously process and regulate the crew's drinking water and their breathable oxygen. Everything is interconnected. Building the service module is a feat of complex environmental engineering. NASA and its partners have essentially miniaturized Earth's biosphere, placing it 250,000 miles away from home. Shortly after launch, while the spacecraft is still coasting in high Earth orbit, the crew will run their first critical interactive test. Artemis 1 relied entirely on automated flight software. Artemis 2 demands that the crew physically pilot the vehicle. They call this the proximity operations demonstration. The astronauts will take the control stick and manually fly the Orion capsule in close proximity to the discarded upper stage of their rocket. They are mapping out exactly how the spacecraft handles in a real-world vacuum. They need to measure thruster authority and see if the capsule responds accurately to small control pulses. Mastering this spatial awareness and proving out the manual controls is an absolute prerequisite. If a crew can't reliably steer the ship here, we can't safely attempt complex lunar dockings on future missions. You might notice that the flight plan doesn't actually include orbiting the moon. That is entirely by design. This diagram outlines a path known as a free return trajectory. It's a route we have only ever executed once before, when it was used as a lifeboat strategy to save the crew of Apollo 13. It is the ultimate failsafe. Once the initial burn puts Orion on its path, the moon's gravity takes over. Even if every single engine on the spacecraft fails, orbital mechanics will automatically slingshot the crew safely back home. But that return journey ends with the most dangerous 19 minutes of the flight, slamming into the Earth's atmosphere at 25,000 miles per hour. During the Artemis 1 re-entry, engineers found unexpected charring and missing chunks of material on the heat shield. That anomaly forced NASA to halt the program, delaying the next launch until they could completely identify the root cause. When a capsule is plunging through temperatures approaching 5,000 degrees, leaving things up to chance is not an option. Thoroughly dissecting and solving these hardware anomalies is the only way to guarantee the crew makes it safely to the surface. Beyond checking off mechanical milestones, the mission is actually structured around the crew themselves. They are the primary scientific subjects. We have been missing a critical set of data for over half a century. Artemis 2 will finally show us how modern human physiology holds up against deep space radiation and prolonged microgravity. And as they loop around the far side of the moon, those 4 astronauts will serve as our eyes, observing and documenting a perspective of the lunar surface that no human has seen since the 1970s. Every step is a deliberate dependency. If the life support holds firm, if the manual controls prove precise, and if the heat shield holds the fire at bay, this crew successfully hands the baton to Artemis 3 to attempt a landing. Artemis 2 marks the shift from proving we can reach the moon to demonstrating that humans can actually live there. By validating these systems with a crew on board, we establish the technical foundation for a permanent presence in deep space.